Wouldn't it be amazing if there was a low power button? Some kind of simple push button that you could press and bam, your new design was 20% more energy efficient. Maybe we'll get there someday. But for now, energy efficiency involves a careful consideration of architectural decisions, power profiles, and software optimization. And you know what can help with all of that and more? Shifting left. Hi, I'm Amelia Dalton, host of Chalk Talk. A shift left methodology can help lower power throughout the electronic design cycle. In this episode of Chalk Talk, William Ruby from Synopsys and I explore the biggest energy efficiency design challenges facing engineers today. How Synopsys can help solve a variety of energy efficiency design challenges, and how the shift left methodology can enable consistent power efficiency and power reduction. And before we get started, don't forget to click that link. There you can find even more information about this topic from Synopsys. Hi, Will. Thank you so much for joining me.
Yeah, you're most welcome. Glad to be here. Thank you for the opportunity.
Absolutely. Okay, so we're talking about end-to-end energy efficiency and how Synopsys is helping solve a variety of energy efficiency design challenges. But Will, before we get started, can you set the stage for us? AI is driving an extraordinary demand for power, right?
Sure. Somebody other than me already said that AI does not run in thin air. And AI takes energy and it takes money. In some cases, you may think that energy is money and money is energy. But what we see is an unprecedented demand for energy from the AI perspective. You see that the increase in the portion of energy connected with AI in the data center is really projected to go up by 4 times in the next 4 to 5 years. That's a huge, huge leap. On the right side, you see some numbers. You see that it takes, per GPU, consumes 400 watts of power. If you start comparing the typical Google search versus a ChatGPT request, but even that alone, the ChatGPT request takes 10 times more power, more energy than a typical Google search. So training a super large language model like GPT-4, 1.7 trillion parameters using 13 trillion word snippets. A company called OpenAI revealed that it cost them $100 million and took 100 days, utilizing 25,000 NVIDIA A100 GPUs. So servers with these GPUs use about 6.5 kilowatts each. So the estimated amount of energy that is required for training is on the order of 50 gigawatts of energy. If it's about only $1 per GPU hour, the cloud expenses alone in this case would be around $60 million. So energy efficiency is absolutely key to the modern design. Targeting these AI applications will require huge improvements in energy efficiency in the design.
So, Will, I've been hearing a lot about shift left these days, but shifting left can also help in energy efficiency as well, right?
Sure. So it's basically doing things earlier in the design cycle, making informed decisions, even during the very early architectural design stages, selecting IP that is energy efficient, even optimizing software or firmware that runs on the device, because software controls how the hardware is operating. So you really need to start thinking about these things very early on, including even profiling the software workloads for power. And then you move to the RTL stage, and now you have more opportunities to do microarchitectural fixes, to look at various types of power consumption bugs. And then as you move down to the synthesis and implementation flow, now you have the automation helping you in terms of optimization and power reduction, followed by ECO, followed by sign-offs. So what happens here is that potential power savings are much higher in the earlier design stages, and they significantly diminish after this inflection point in the middle, which is really the synthesis inflection point. So before logic synthesis, you have lots of headroom to optimize the design. As the design gets synthesized and implemented, your headroom decreases, the number of degrees of freedom decrease, but you have now more automation to really squeeze out the last 10 to 15% of power.
So, Will, what are the biggest energy efficiency design challenges you're seeing these days?
Sure, that excellent question. So there are several things here, and what you see is that as the industry have moved down from what are now called mature nodes at 130 nanometer down to 90 nanometer, at some point we recognize that leakage power has become important. And of course, timing before that was really the key goal. Power was really a distant second. But then as we move down to the technology nodes, leakage power has become more and more important. Well, as we move further down through the innovations in process technology, we're now are able to control leakage power and bring it down to a more manageable level. But then as we move further and further into the angstrom era, what you see is that other physical effects and design issues come in. For example, glitch power, where glitch here is really defined as multiple transitions on a given net in the clock cycle. And that fundamentally is wasted power. Power analysis is fundamental to the overall methodology. And what we see here is that the traditional methodologies of using synthetic or artificial simulation vectors miss real world conditions. They miss the peaks, they miss the sustained worst case operation because they fundamentally do not represent a real workload. And on top of that, of course, the designs like the GPUs that I mentioned, they're not getting any smaller. So what we need then is we need a massively scalable power analysis solution that not only takes into account large workloads, but obviously huge design sizes like modern CPUs and GPUs.
So, Will, how can Synopsys help with increasing energy efficiency?
Well, I've always said that power is an equal opportunity problem. Everybody can contribute to the solution. And what I mean by everybody here is that if you see in this picture, this is the Synopsys energy efficiency solution. And what we did here is we mapped different capabilities across different parts of the solution to be consistent with the previous shift left picture. So now you see that the solution is spanning the space between architecture to RTL design and RTL verification, emulation, going down to implementation and test, and then finally, final ECO optimization, and we call it last mile closure, the Foundry certified power sign-off, which is certified to be within a few percent of SPICE results. So that's the overall solution, just like what you saw in the shift left slide early on in the design stages. You're looking at basically what if type analysis, you're looking at exploration capabilities. This is where you make significant choices in terms of your architecture, in terms of IP selection. Software workload power profiling is really important at that stage. And then later, as you go through the implementation flow, now you have more opportunity to utilize and take advantage of automatic power optimization. It's done within the full power performance area set of constraints and really drive the full closure of your design.
So, what kind of power reduction results are we looking at through the entire design cycle?
Yeah, that's a really good question because ultimately the proof is in the pudding, as they say. And what you really need to look at is what are these power improvements or energy efficiency improvements? So this gives you an idea. And let me pick on one example in particular. A company by the name of SEMA.ai published a paper at the Synopsys user group meeting where they showed us that they were using Synopsys technology specifically for software workload power profiling. They were able to understand what the software behavior was from the power perspective. They were able to optimize their hardware architecture. They were even able to improve their compiler that they use to compile the software into the executable. And altogether, what they showed and presented at the user group is that over several months of multiple iterations per day, different types of architectures, they were able to achieve a 2.5 times improvement in energy efficiency, which is really, really significant. So that's one example. But then you also get into other areas where more of the automated optimization comes in, tool guided and automatic optimization at the RTL design stage during the synthesis and implementation flows. And you see here that different types of designs, so image sensors, NPU type designs, are getting 20+% power savings as well. But this kind of gives you an idea of what is achievable within the Synopsys energy efficiency solution.
So, power analysis is fundamental to the energy efficiency methodology. What are the specific issues with power analysis?
Yeah, power analysis is fundamental. You cannot optimize what you cannot measure. So you need to really have a good power analysis methodology. But what happens with power analysis is that it has been traditionally driven by simulation scenarios. So you get RTL regression vectors, which are really synthetic simulation based tests. They are maybe not covering the complete use case, missing the real world interactions or real world scenarios. And this is actually a slide that was presented by Meta at the Primetime SIG event. And this is what they showed. They said, look, if we just rely on simulation-based power analysis, it's not really sufficient. It doesn't give us the coverage. It may point us to the wrong area to optimize because it is artificial. So what they're advocating is instead using the actual software workload to do this power analysis. So they run a real use case in the emulation environment, getting a workload that represents tens of millions, hundreds of millions of clock cycles, and then they use the workload with a power analysis tool to really get a realistic picture of what their power profile looks like.
So, can you walk us through how Synopsys tools can help with these kinds of workloads?
Sure. The specific solution that we have for workload power profiling is called ZeBu Empower. And as the name implies, it is designed to really work very closely with our ZeBu emulation and prototyping hardware platforms. So what happens here is that you would run your RTL emulation on the ZeBu hardware box. You instrument it with your workload, represented here by the software scenario. And then the ZeBu hardware would generate an activity database called ZTDB. This activity database represents that workload. So it's the activity associated with a specific software workload running on your RTL description of the hardware. And then that workload then gets to be an input to ZeBu Empower. So ZeBu Empower takes as an input also the same RTL source as you are emulating. You provide constraints, you provide synthesis libraries, and ZeBu Empower is able to give you a power profile potentially over billions of cycles long. ZeBu Empower is massively parallel. It scales very well with a number of CPUs. So you can literally run this power profile on hundreds of CPUs and get a very reasonable turnaround time. And in fact, I referred to SEMA.ai just a few minutes before. And then here's a quote from their CEO that says that it's the Zibo Empower solution that enabled them to drive that 2.5x energy efficiency improvement. On the right side, you have a note from AMD that is really heavily using the Zibo Empower solution for their EPIC processors.
So, can you give us some more details on power profiling?
Yeah, when we say power profiling, what does that really mean? What are the things that you can look for in a power profile? So here's an example of what the power profile looks like. And this is an example of a power profile, again, over hundreds of thousands, I think even millions of cycles. So, what are some of the things that you can glean from such a power profile? So, first of all, you see in the middle here, power substantially goes up and then it stays at a pretty high level, and then eventually it comes back down. The middle portion here, that is really where you can say, this is my sustained worst case operation. So this is like with a heavy traffic load, a lot of computation all going on at the same time. So the sustained worst case, you can use that to do some early budgeting for your thermal analysis, whether it's for package selection, heat sink selection, cooling subsystem, and so on. So that sustained worst case will give you an idea of what the power level is in order to do those calculations. The same is also for, if you're interested in peak power for IR drop reasons, you can detect where in this profile you have the peak power cycles. So you can see that we identify where the peak power is. On the bottom left side, you have a reset sequence in the beginning, and then you have an idle period, and then all of a sudden you have power consumption going up for a short period of time, and then going back down before getting to that sustained worst case. So that increase in the power consumption, supposedly the idle mode, could be an example of a power consumption bug, that you may have some portion of the design that is being activated where it doesn't really need to be active. So therefore, that would be something that you can investigate and see if you can eliminate that power consumption bug. So other than the sustained worst case, if I want to know what is my typical average power consumption, let's say this is a mobile device, I want to estimate my battery life using typical average numbers. And on the right side, you have that segment where you have a typical average power consumption. So bottom line is that having a realistic workload-driven power profile, you can glean a lot of information related to power consumption of your design.
So, Will, what does the full methodology look like with realistic workloads?
Interesting area. And we at Synopsys really have this concept of a reference methodology. In this case, we call it a vector funnel. The reason why this is called a vector funnel is because you're starting out with a very long profile. So you can identify different regions in your profile, whether this is your sustained worst case, as I mentioned, whether it's an idle mode, peak power conditions, and so on. So you're starting out with a large amount of clock cycles. Okay, now I want to direct my implementation and optimization efforts for specific purposes. Like, for example, I want to optimize my design for sustained worst case operation because I need to drive down my thermal design power. So you can carve out that portion of the power profile, feed that activity associated with the sustained worst case operation into your RTL design flow. And the RTL design flow will then take that activity, and other Synopsys solutions like Prime Power RTL, RTL Architect will use that information and target the optimization efforts for that specific portion of the activity. So with Prime Power RTL Architect, it's an RTL design phase. So the tools will give you suggestions about rewriting the RTL. They're not going to output RTL for you, but they will give you suggestions about improving the RTL for power, improving clock gating efficiency, looking at the memory subsystem operation, see if you have any redundant memory cycles, redundant reads, redundant writes, and so on. With Fusion compiler, again, this would be a full optimization in the power performance area context. And we have this notion of an activity refresh flow with Fusion compiler and prime power that will give you some additional benefits. And then with prime power as the certified power sign-off tool, it is highly accurate, but it is not really targeted to analyze billions of clock cycles. So the idea here would be to pick out specific intervals from the overall workload and the overall power profile to say, for my sign-off, I want to analyze these specific portions of the workload, whether I'm signing off to say this is my sustained worst case, or I need to know what my final sign-off peak power is. All of that can be driven in this vector funnel reference methodology.
So, as an example, with prime power activity refresh flow in particular, what kind of PPA benefits are we talking about?
It's a very interesting flow in the sense that what you have to realize is that as the design is going through the physical implementation part of the flow, it is actually not a monolithic or push button type of a operation, single pass, but it actually goes through stages. You have the initial synthesis as part of the implementation, then you have placement and placement based optimizations. You have clock tree synthesis, and you do the final detailed route and even post-route optimization. So the idea here is that your seed activity into this flow is your RTL simulation. It could be the emulation power profile, a segment of that from the ZBOM power solution. But you have that starting point. But the fact of the matter is that during these implementation stages, the design itself changes. So you have buffering, you have some logic restructuring and things like that. So the activity that you had to begin with is now stale, meaning that it's not really updated. In order to do a really good power optimization in this flow, you need to recompute activity based on the netlist stage that you're in, whether it's post-placement, post-CTS, post-route, and so on. So that's where this activity refresh flow comes in between prime power and Fusion compiler. So prime power will take a netlist. It'll be able to quickly recompute activity on that netlist and then send that activity file called the save file, switching activity interchange format, a save file that basically has the updated toggle data back into the implementation flow. So this activity refresh then is really important to get the best possible power optimization results. So you see here several designs were compared to a non-refreshed flow. We are seeing anywhere from 4 to almost 10% power savings. And that's very significant and over and above everything else that has been achieved early on in the design flow through architecture, IP selection, and so on.
So, Will, to wrap things up, what would you like my audience to take away from today's Chalk Talk?
What's really important to keep in mind is that there is really no such thing as a low power button. I cannot push a button and all of a sudden get a low power design. Driving low power, driving energy efficiency requires that you really adopt this shift left view, that you really need to start early on in the process, looking at your architectural decisions, even looking at your software-based profiling, understanding where your trade-offs are, and ultimately coming up with the best combination of architecture and software at that point in time. Now, besides architecture, you really need to follow that through the rest of the flow with this vector funnel methodology that gives you that consistency. It uses realistic workloads for everything that happens downstream, whether it's RTL power analysis and power reduction, whether it's synthesis and implementation optimization, and the final sign-off. All of that can be driven through this vector funnel methodology that really drives this activity throughout the flow. And that's really emphasizing the point about the overall end-to-end energy efficiency solution from Synopsys. It's realistic workload driven, and it covers the entire space of architecture to RTL to implementation and finally sign-off.
Excellent. Well, Will, I think that's all I have time for today. Thank you so much for joining me.
Thank you. This was a great opportunity, and I really enjoyed going through this material.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Synopsys. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.